So in a classical gate circuit, we have an answer that's either going to be 1 or 0. But the whole point of doing this in a quantum computer is that you can have some probability that it's 1 or probability that it's 0. And we call this the state vector, the likelihood of different outcomes that we would get by measuring the system. So we're going to set up a system and we're going to do all the superposition manipulations, and then we're going to measure the system, and we're going to get a spin up or a spin down, right? The particle at the end of the day can be in one or the other of those states. How we measure it depends on what we're looking for, and the end result is that it's going to be some of the time in 1 and some of the time in 0. And the problem there is that we don't actually get any information about what the likelihood of it would be just by measuring it once. We have to measure it over and over and over again. We have to do the experiment many, many times with the same settings, and sometimes we'll get a yes, and sometimes we'll get a no, right? Sometimes we'll get an up, sometimes we'll get a down. And we do that over and over again, and then the distribution of yeses and nos gives us information about the underlying superposition state vector. That's what we're trying to get at, is what is the state vector that existed before we collapsed it by measuring it, right? Because remember, this is all superposition, and when we measure it, we collapse the wave function. But we want to know what the wave function was before we collapse it, and so we measure it over and over and over again. Here's a really simple example of a single qubit that I can either be 1 or 0, and thinking about the way that the state space is represented. So if I put the possibility that the result is 1 up in this direction, and I put the possibility that the result is 0 over in this direction, then I can imagine a vector somewhere between 1 and 0 such that it represents the likelihood that it's going to collapse to yes, 1 or 0, collapse to 1 or 0. I have to measure that by measuring either 1 or 0. I put my measurement device, my detector, and that detects whether or not the quantum qubit is in the up position. Is it 1? That's all I can measure is it 1? And I get a yes or I get a no, right? If it isn't, then I get a no. And looking at the way that this arrow is positioned, more of the time I'm going to get a 1 than a 0, but sometimes I'm going to get a 0. And so we measure it over and over and over again, and we do it enough times that we can infer what the A and the B coefficients were before we collapse the wave function. And that's the whole premise, is that we want to set up a state vector, a state variable, such that we can do some interesting work, measure it a whole bunch of times, and infer what the superposition was before we collapsed it. So that's for a single bit system. In general, for an n-bit system, the state vector is going to be a 2 to the n dimensional quantity, right? If this is a one-dimensional quantity, is it yes or no? This is going to be a 2 to the n dimensional quantity, which is the same as with classical gates, right? If you have 3 bits, for example, there are 8 possibilities. But now with a quantum computer, if we have a 3-bit system, we have the likelihood of each of those 8 possibilities. And so each of those 8 possibilities is going to be a different direction in vector space. And when we do our manipulations, we're going to check the likelihood that we get a 0, the likelihood that we get a 1, likelihood that we get a 2, all of those different values. And then the whole point is, if we can manipulate the superposition such that the likelihood of the answer we're looking for is fairly high, then we do the operation a bunch of times, we measure which output was the highest likelihood, and that gives us our answer. Now, the way that the state vector is set up, we have the high dimensional space, right, where each sort of direction, x, y, z, each of those directions represents one of the possible outcomes. And as it turns out, the likelihood on each of those directions the square of the likelihoods sums to 1. And this is coming from a quantum physics idea called the Born rule, which is that the probability and outcome is the square of the state's amplitude in the direction of measurement. So if you're measuring up and you get a certain value, right, we get a certain number of times where we get a successful measurement of up, we square that to get the probability, the underlying probability of the state vector, or in fact the other way around, right? The superposition, the wave function the square of that will give you the actual probability that you're going to measure up. Why is it the square? Well, it's difficult to explain. If you ask a physicist, they have different explanations for why this is the case. But the reality is, when we do the math, when we do the experiments, square is what we get. So we get the square of the wave function given the probability of the outcome. So this is actually how we get the power of quantum computing. If we have an n-bit quantum computer, we're doing n measurements. Each is either going to be yes or no, right? Because we're measuring in a certain dimension, whether the spin of the particle is up or down. We're doing n measurements, and we're going to produce these probabilities just like a classical circuit, right? Again, 3 bits gives you 8 possibilities, and then the likelihood of each of those probabilities gives us the answer. A classical circuit gives a single value every time. A quantum circuit is going to result in the probability of different values, and this is going to be where we're going to be able to do our math. Just a little bit more background, and then we'll actually get into it. One of the ways that we represent what we think the underlying superposition is called a Bloch sphere. This is a representation of the likelihood that the bit is going to collapse into any one direction. It turns out that in order to accurately represent the superposition probabilities, we have to use complex numbers. And again, it's sort of like the Born rule, like the Born rule, that this is the way it works. If we do the math with complex numbers, we get the right answer. And that's the basic premise of how we know that it's complex numbers. And so the interactions between these states only work if we use complex numbers. We can represent those complex numbers in a 3-dimensional sphere that is a combination of whether or not the individual qubit is 0 or 1. Right, the amount of the probabilities that it's going to be collapsed into any particular state. So here is a few examples, and again, this is from this Algazert example. If we start with, so if you remember, that first one up there is the swap gate. So if we start with 2 qubits, one of which we know is in the up direction, and one of which we know is in the down direction, then if we swap them, we get the opposite Bloch spheres. Right, we get the representation where the top qubit is now in the down position, and the bottom qubit is now in the up position. Same with the single complement, the C naught. If we start in this example with 2 qubits in the down position, then the qubit in the top being in the down position causes the qubit in the bottom to be flipped into the up position. And then here's another example with our Toffoli gate, right? 2 inputs that control whether or not that bottom one is complemented. And it'll flip based on the value of those different bits. If both of them are down, then that one will flip. These examples are all, there aren't any superposition. Everything is exactly either 1 or 0. And again, later on, I'll show you what those superpositions actually mean.